Hello everyone, welcome to today's video. In this video I will explain about how to identify material parameters for Johnson & Cook plasticity model, and I'm going to show you two ways of doing it. One is using Excel because it's generally is a uniaxial case, so you can survive with Excel as well. It's one-dimensional problem in reality. And also how you can do it in Abacus, which is more tedious way of doing it unless you know Python. So I will show you one way of how to do it. But if we are using a Johnson & Cook plasticity model, it has a strain hardening which has three parameters, A, B and N, dependent on the equivalent plastic strains. And then there's a strain rate sensitivity or strain rate dependence term, which is given by this bracket here, and you have two parameters involved, C and epsilon naught dot, which is a reference strain rate, while this is a plastic strain rate which is dependent on the loading itself. And then obviously the thermal softening part, which will be irrelevant for this case because we are more concentrating on the strain rate dependent case. But if you have stress strain curve for different strain rates, as you see here, I have 5 strain rates from 0.001 up to a strain rate of 100, and then you will have curves for different temperatures as well, so it gets more complicated as well, especially when you do it in Abacus, because you will have to create a number of jobs for individual tests you have to do in Abacus, which as you have done in experiments, and that can take a long time to do if you do it by hand or manually. So if Python is must for those kind of tests, and you can automate the process using Python easily. However, in Excel you can directly do it, and I will show you one way of doing it for strain rate dependent case and not the thermal softening case for this problem. So let's jump into the real business and see how we can do it. Okay, in the first part of the video I will first start with an Excel, and I will show you how you can identify parameters for Johnson & Cook model using a simple Excel sheet, and then I will take you with the same model parameters to Abacus and show you that the model parameters which you have identified from Excel really works in Abacus, or if you need to change anything in the parameters. So let's start with that. So let's see on the screen, you can see the parameters which are visible right now, and as you can see, we are assuming it again, these are fictitious values. I have just fabricated the data using some analytical relationship which are very similar to Johnson & Cook model, so you will get a very good comparison once we identify the parameters. So we have 5 strain rates in this case: 0.001, 0.1, 1, 10 and 100 per second, right? So we are and this is the data for that. If you want to plot that data, so I can go and try to plot it with simple graph here. It may take some time, but it's good to show that, so I will just remove everything from here right now. So now we have these for 5 different strain rates, and you can see as you increase the strain rate from left to right or from top to bottom, your stress strain curves are changing. And again, it's a plastic part, so we are not really worried about the elastic part at this point. Okay, so now what we have to do is we have to identify Johnson & Cook model. So I have created another sheet, and here if you see, I'm using the same strain values from my previous experimental data, and in this case obviously this was all from experiments, while in this case I'm computing the stress using the same relationship. If you remember, it was A plus B times epsilon raised to power n. So A and B are these constants here, and B3 is basically the strain, so strain raised to power this n parameter. And then I had 1 plus C, so C is n4 times natural logarithm of epsilon again, and that's a strain rate epsilon dot, so in this case it's B1 for example, dot over the parameter which was epsilon naught dot, right? So these are the parameters. If I vary those now based on these definitions, so I have done it for all the 5 cases. only thing which changes in these cases is the strain rate, which is given here, okay, in the second part of the equation. So $D1 is basically the strain rate. For this case it should be $F1, so you see it's there. So now I start to fit these curves. So you see they're already there, but you will start with some values and you will start fitting it. So this is for the all set of values with the model and experiments, and this graph, again you can plot the graph as I showed you before in this here. So you can just plot all the graphs in one go. And this is only for 0.001 to fit that first, and then start with this. So I will also suggest that first start with one of the curves and try to find A, B and N value in an approximate way, and then start playing around with the strain rate sensitivity parameters. So in this case you see there is some differences, so I have played around with that. So let's try to bring it close to much closer. So let's say change it to 25. So you see curves start to shift up a bit, or maybe 26 for example, and it's further close, but you see my my experiments are still below above this for the higher strain rate. So maybe increase further, or maybe increase the hardness, which is B parameter here. So let's make it 280, and you see it's trying to get closer to that. Also I can play around with 0.31 maybe. So what happens, so you see it's a perfect match, and I was able to fit all the parameters for strain rate cases as well after changing C and M. So if you see, I have already fixed those parameters, but you can start with any guess, let's say 0.1. So you see there's a difference, and also you can start with 0.001 as a reference strain rate, and then you can also play around with that. So for example, you can see if I change it to 0.2, it starts to further go up, so I need to decrease this value rather than increase it. So let's say 0.1, which is close, so further reduce it, so 0.08, and you see it's coming back to that. Again, you can have multiple combination of these parameters which can give you the best fit. So again, you can decide based on that, but try to see, I mean, this will be more close to the A parameter, it will be more close to the yield strength of the material at the reference strain rate. So maybe start with these parameters and then move to this one, 0.75 I think, oh sorry, 0.075, and you see we are very close now. So again, you can increase further, it's going away, so maybe decrease. So you see it's almost a fit now. So this way you can identify the parameters, and now you have a set of parameters for A, B, C and C, okay, and epsilon naught dot. So once we have this, now we can go in ABAQUS and do simulations for these strain rates with one element in a uniaxial setup, and then see if these parameters really give me similar curve or not. So now let's go to the ABAQUS and see if we can do that. So now we are in ABAQUS, and you can see I have already created a part, but for those who are not familiar, you can just create a part by pressing create part button, 3D deformable solid extrusion, and then I just created a rectangle from whatever, and then I give a extrusion depth, let's say 1 or something, and then that will give me that picture. So it's 1 by 1 by 1 thing, okay. So that's what you see here as a part 1. So this is my part, and that basically is 1 by 1 by 1 cube. Property is more tricky in ABAQUS because in the Excel case we didn't require the elastic constant, but in this case ABAQUS will ask us to define the elastic constants. So I'm going to use any fictitious value for the time being, and let's say I can use a value of 200, since everything is in millimeters, so 200 gigapascal, and then 0.3 or something for a metal. I'm assuming it to be a metal. And then for the plasticity, I can say I'm using plastic, and then I can select Johnson and Cook parameters, and here I have to define all these parameters A, B and C. So again, I can take those parameters directly from my Excel sheet. It's 26 to 80 0.31, so 26 to 80 0.31. For M, I don't need M right now, so I'm just going to use a value of 0, because I don't need anything. Again, I'm just using 825 and transition temperature to be 25 or something. I don't know what it's gonna do, but so these are the parameters I required. I have to have a rate dependent potential, so I need to define that. Again, I have different options here for rate dependency, and I'm going to use that option where I need to identify C and epsilon dot. So C is 0.073, right? So 0.073, and this one was 0.001. All right, so my material parameters are now defined as I require, but I will have an additional elastic part, so I need to pay attention to that. Okay, and then I create a solid section, material 1, and then I assign this section to this element. Color has changed, so this means properties are assigned properly to this part. I will go to the assembly. I will bring this part or instance this part here, and I don't need any more further assembly operations because it's only one part. For the analysis, again, I have two options. I can use static or dynamic. So let's start with static. I am not sure if it's going to work, but let's do it. And you can see I have increased in the maximum number of increment in case it struggles, but though I don't think so it will be a problem. It's a simple nonlinear material analysis, and I'm using 0.1 as the maximum time increment to get at least 10 outputs if I'm running it for total time of 1 second. All right, so no interactions are required. I'm going to go to the job, and now I'm going to apply boundary conditions which will replicate our which will be a representative of our typical uniaxial test. So in this case, what I will have to do, I will fix, for example, this surface in X direction. I need to keep two surfaces free. Then I will apply another boundary condition. I will make this surface to be fixed in Z direction, and top or bottom surface I can fix in Y direction. So I prefer to have a bottom one, so you can rotate, you can make it display, and then you can select, and then you say okay, U2 should be 0. So now I have everything ready. You can bring it back to that, and now I'm going to pull from any one of directions. So let's pull it in the Z direction. Okay, so if I go here and if I pull in Z direction, and that will be in U3 direction. Again, I need to be careful with the rate sensitivity here. So let's start with 0.001. So all right, so to work out the displacement now, we basically need to find out the total displacement I need to apply in 1 second to ensure that my strain is 0.001. So, and since I have to go up to a total value of, for the case of this, around 0.06, so this means I need to apply a total displacement of 0.07. I'm just assuming it to 07 because I have some elasticity there as well, but I need to apply this in certain amount of time that it becomes the total strain rate becomes 0.001. So what I do now is I can just use a calculator here. All right, so I have applied a total displacement of 0.07, but I need to apply it in such a way, in such amount of time, that my strain rate is around 0.001. So if the strain rate is the strain over the time, and I need to find the time, then I need to divide this with the strain rate. So if I divide this with the strain rate, I will get 70 seconds. So again, this will take a long time, but let's try that. Edit, and I change it to 70 seconds, and then obviously it's not a good idea to have it time input as 0.1, so maybe I will keep it to 1 second or something, or maybe 2 seconds as a maximum. Okay, and so total time is 70 seconds. Now I go, my loads are okay, but the problem now is I have applied it in the compressive direction. So I will go and I will change the direction. So I just need to change the sign of this thing. Once I have done that, I go to the mesh, I apply seed to this part, so you need to select the part rather than the assembly first. Then I'm going to give an element global size of 1 because I only need one element in this case. I'm going to mesh it, and I will see what is the element type here because I need a static 3D stress element, and I'm using C3D8R. Okay, so which is default in this case. And then I go to the job, and if everything is defined correctly, then I can create JC test1 JC test 0 underscore 001, and then I will just create a job and submit. It should not take very long, but let's wait for it. So as you see, it gives me an error, and just because I did everything so quickly that I forgot that the temperature should not be the same, otherwise it will become infinite because it's theta melt minus theta transition. So maybe I will use this as 0 as I'm not initiating any temperature, and now it should work, I think. Or to be on the safe side, I would prefer to use a high value for this. Let's say 500 degrees Celsius. Okay, so now I go back and run again, and hopefully this time it should be running okay. So now you see it has started the input file processor, which is completed. So now input data is okay, and it has started analysis, and you see it's going pretty fast now. I gave it the initial increment to 0.1, and maximum was around 2, so it is reaching towards 2, and then it will be quickly going towards that. So as you see now, analysis is finished. Total time of 70 seconds. It hardly took a couple of minutes to simulate this on a normal PC, so it was pretty quick for one element. And now I go to the results, and firstly I will see the deformation and see my tensile loading is acting properly. So you can see it's pulling in this direction and it's contracting in the normal to the two surfaces. So everything worked fine as I required. And now I'm going to create an XY data, so S33 and logarithmic strain 33, and we'll see how it looks like. It should be close to what we saw in Excel. So let's look for LE33 and also S33 because yeah, stresses are there. And then we select the element. So I select this one and then save the data. So data is saved now, hopefully. So if I go now to manager, XY data manager, I can see stresses and strains. So I will just combine them to get a combined plot. Otherwise, right now they will be plotted as a function of time. So I need to plot stress as a function of strain. So I will go to, sorry, not this. So I will go to operate on XY data because I need to now combine them. And I will select combine, and I prefer always to use absolute because my stress or strain can be negative based on the direction or based on the type of stress, whether it's tensile or compressive, depending on the boundary conditions. I'm avoiding that, and then I apply this. So now if I save it as XY whatever data, and if I plot this, so it should look something like this, and you see it's pretty much what we expected. So if you remember, my stress strain, my yielding should have started at around 20 something, and it should have gone up to this value for this. So again, we only need up to 0.05, so I can change the scale to 0.05 here, and so that's how it looks like, right? So now if you look at the Excel, if you remember Excel plot, it was like that, and it was also going around 140 or something at 0.06. Okay, so we can plot 0.06. and it's also going the same way here. Okay, so 0 point something, so sorry, yeah, so it's also going up to those kind of values. Yeah, so let's do 170. All right, so it's around 0.147 or something, while what you see here is around 140 something as well, so 145, 146. So you see, what we identified here works in 1D case, but if you have complicated loading, your tests include biaxial or triaxial loading, or there is a complex interaction between lateral and direct stresses or normal stresses, then you might have to directly do it like I have done it here in ABAQUS. In that case, what you will have to do is you will have to basically create these models. Let's say you have to create 5 models here with 5 different materials, and then you have to change the parameters one by one, run all of them together, and plot the curves as we discussed in my previous video on material modeling and material parameter identification. But then it's a tedious job, so I think Excel is the best bit for uniaxial cases, and you can see we got a very good fit for all the cases, and we got a confirmation from our ABAQUS simulation as well.